Picture a spacecraft re-entering the Earth's atmosphere at 10,000 miles an hour. To measure this, physics usually starts with scalar quantities. A scalar is a measurement of pure magnitude. It tells you how much or how fast. Mass, volume, and speed are all scalars. But knowing that a spacecraft is moving at 10,000 miles an hour is useless if you don't know where it's pointed. Speed alone won't tell you if the ship is safely approaching a landing coordinate or skipping off the atmosphere into deep space. Scalars are great for taking inventory, but they fall short when objects actually move. To map destination and intention, we need an entirely different mathematical language. We solve this spatial problem using vectors. A vector is a physical quantity that explicitly possesses both a magnitude and a direction. Look at this basic vector diagram. It's represented by a single line with an arrowhead. The starting point is called the tail, or origin. The tip is the terminal point, and the actual physical length of that line represents the sheer magnitude of the force. Sometimes we only care about the trajectory, independent of scale. If we reduce the length to a magnitude of exactly 1, we get a unit vector. It represents pure direction. On the other extreme is the null vector. If you multiply a vector by 0, it loses all magnitude. It collapses into a mathematical anomaly, a point with an arbitrary, undefined direction. By understanding these structural components, the origin, the length, and the direction, we establish the raw materials required to map any isolated force in the universe. But physical forces rarely act in isolation. If an aircraft flies east and a severe crosswind pushes north, how do we calculate the actual path of the flight? We calculate this using the law of triangle addition. If you place two continuous vectors head to tail, you can draw a third line from the start of the first directly to the end of the second. This closing side gives you the exact resultant vector. Vector addition is strictly commutative. Whether you add vector A to B or B to A, the physical outcome, that diagonal path right down the middle, is perfectly identical. Still, manually drawing triangles for every gust of wind or gravitational pull quickly becomes exhausting. We need a standardized mathematical framework to tame these interactions. This chart demonstrates how we place a diagonal vector onto a 2D Cartesian grid. We can break that chaotic diagonal force down into specific x and y components. By taking the interior angle, theta, we calculate the horizontal force using cosine, and the vertical force using sine. To measure these newly sliced components, we use orthogonal unit vectors, standardized mathematical rulers along the x and y axes, typically written as I hat and j hat. Slicing vectors